channel. So today we are starting with the new chapter, that is effects of electric current. In this chapter we are going to see the topics energy transfer in an electrical circuit, heating effect of electric current, applications of the heating effect, magnetic effect of electric current. In that topic we'll have further topics related to the magnetic effect, that is magnetic field due to a current carrying conductor we are going to see. We are going to see solenoid, we are going to see electric motor, galvanometer, electromagnetic induction. We'll even see electric generator. All these topics would be covered in separate videos. Okay. So we are starting now with the first topic, that is energy transfer in an electrical circuit. Okay. So basically what we are going to see is nothing but the electrical energy. How is the energy calculated in an electrical circuit? For that first we need to revise our Ohm's law. Okay, we are revising the Ohm's law first. What does our Ohm's law tells us? See, a very basic, we are going to consider circuit, right? This is suppose is my cell. This is my plug. This is my resistance and meter I am considering. Okay. And now I am attaching a potential V across it. Okay, potential of V across it. This is plus, minus. Fine. So what I see the current I is passing from A to B in this direction. By the Ohm's law, what we know, and the potential difference between point A and B is V. So we know that this potential difference is equals to the current in the circuit into the resistance. This conductor has got a resistance R. Okay, this is given by the Ohm's law. Now what do we mean by the current? What do I mean by the term electric current? See, the flow of electrons is nothing but the electric current. Is what flow of electrons. Fine. Now what is my voltage? Voltage is the potential difference because of which the electrons are flowing. See, for the work to be done or for the electrons to flow, okay, there is this voltage difference because of which the electrons are flowing. Okay, in this case electrons flow when I consider electric current is from the negative potential to the positive potential. I am going to tell you why. For now we understood the very basic point is electric current. What do I mean by the word electric current? My I is nothing but flow of electrons. My V is the potential difference. See, the reason why the electrons flowing is what? The potential difference. Okay. Now we are going to see next why the electrons flow from negative or lower potential to the higher potential. Let me erase this part. Very small concepts I am clearing first. Why electrons flow from lower potential to higher potential. Okay. Now see, when I am talking about voltage, positive electrode and this is my negative electrode. Okay, I am talking about voltage V. What do I mean by the word positive electrode? This is a positive charge carrying region. Okay, over here positive charged region it is. Okay, and this region is carrying negative charges. Electron is negative charges, right? That's why it would flow from this point to this point. That means it's going to flow from the lower potential to the higher potential. Okay. Now see, this is done, right? Why the electrons are present. Now what do I mean by the work done? What is an electrical work done? Or electrical work done I can say, or electrical energy used. This we know in our daily life, we always use the electrical energy. So now we'll be able to find out how much of electrical energy we are using. Electrical work done or electrical energy used. All the electrical appliances use electrical energy. So first we are studying that only. How is that electrical energy used we can calculate. Okay. See, by the definition of the electrical energy used, what it says, this is my W. Electrical work done is nothing but given by W. Okay. We say that 1 joule of electrical energy is used when a current of 1 ampere. Okay. I am moving a current of 1 ampere across a potential of 1 volt in time 1 second. This is how we can remember. Okay. What we say, that electrical work of 1 joule is done when we move 1 ampere of current across this potential difference of 1 volt in time 1 second. This is a definition of 1 joule of electrical work done. So what becomes my general definition of electrical energy? When a current I is flowing across a potential of V in time T is my electrical work done. Very important. Okay. What we are going to say? Now I can describe my electrical work done as how? Electrical energy used, or electrical, when a current I is flowing across a potential V in time T. Okay, this is my electrical energy used formula. Now see, we know what is a current. Current is nothing but charged per unit time. So my Q becomes equals to what? I into T. Correct? Now instead of this, can I substitute VQ? Fine. So my electrical work done is equals to the charge multiplied by the potential difference. Now see, this resistor is giving the energy, electrical energy. Who is giving the resistor electrical energy? This cell is giving the resistor electrical energy. Cell gives resistor electrical energy. Okay. Correct. The resistor is getting the energy from the cell in which form? By the help of charge Q. Through Q, the resistor gets the energy from the cell. Okay, this much we have to remember. Now next is electric power. Now how do we define the word electric power? Now this we are done, right? It's a very simple formula. We are going to use the electrical energy, right, and derive that formula. See, electric power, I'm going to name it as P, is equals to the electric energy used upon time. Okay, is my electric power consumption. Fine. Which we do on a daily basis. How we are going to find out our power consumption? P is equals to electric energy used is W upon time. Now what is my W? My W is VIT upon time. See, okay? This gets cancelled, so I get VI. Fine. But by my Ohm's law, what is V equals to IR? So can I substitute the value? I'm going to get I square R is my power consumption. Fine. Now we see from this formula. See, electric power is P is equals to electric work done. That is in joules. Okay. And time is in seconds. So this joule upon second is given a special name watt. Okay, so its SI unit becomes what? Joule per second equals to watt. Watt is given is the SI unit of the power, electric power. Okay, now see, we are going to see again, take your work done. W is equals to what? VIT. Okay, now instead of V, we are going to put what? V is equals to IR. Let me put that. So my work done becomes equals to I square R into T. So what I am trying to say is the more electrical energy used when we have a higher resistance, and it's equal directly proportional to the current square. Okay, so that's what we are going to see. Fine. Now next we are going to discuss is commercial electrical unit. Now see, you take out your electricity bill and see how they describe the consumption of electricity. They have given it a specific name, that is units. They count a units. Now what does this word unit means to them? See, this watt is a very small unit. This is very small. So what they have done, they calculate how much of kilowatt is used in a 1 hour. Okay, that's how they remove the bill. Okay, electricity bill is counted in units, and 1 unit is equals to 1 kilowatt into 1 hour. Okay, that means what kilowatt means? 10 raised to 3, right? And watt is what? Joule per second. Now convert this 1 hour also into seconds. 3600 seconds. So equals to what? 3.6 into 10 raised to 6 joules. The seconds gets cancelled. So 1 unit means how many joules of energy we have used? 3.6 into 10 raised to 6 joules of energy. So our electricity bill, they calculate into 1 kilowatt into hour. Like that their units goes on increasing. Suppose we have used 6 units. That means what? 6 multiplied by 3.6 into 10 raised to 6 joules of energy we have utilized. Okay? So this was the energy transfer in an electrical circuit. So if you like my video, do give a thumbs up, subscribe to my channel, and do not forget to share it with your friends.